On the Idaho Falls campus. This is the building, the Center for Advanced Energy Studies building, kind of a joint venture between Idaho National Lab and the Idaho State Universities. I would say that we have the overwhelming number of our graduate students are the largest number of students that are in the case building. Just to say a little bit about the building itself, it looks like it's a little bit floating. All the student cubicles are on the first floor and the second floor along these windows. And all the walled offices for faculty are kind of in the interior. This side that you see in the forefront is they're all office space, and then the back half of the building is on both floors are the research labs. Yeah, it's equally shared by Idaho National Lab staff. They tend to come and go, but there's actually two centers, Center for Advanced Modeling and Simulation from the Idaho National Lab and the Center for Space Nuclear Research are located in the case building. So we have University of Idaho, Idaho State University, and Boise State University faculty and staff. So it's an interesting initiative. It's completely outside the fence, so you can come and go. Whereas, only not even a half a mile away are some Idaho National Lab buildings. It's kind of on the very north end of Idaho Falls. On the back side, actually, is just down the hill is the Snake River. So, thanks for coming. I wanted to the Fukushima, the quake, and the tsunami, and then the accident started on March 11th. That's why I said it's about day 60. Really turned out to be, well, I started making some slides right at the onset, and I now have more than 100 slides. The accident is still, or the situation is still ongoing. I'll show you in a later slide, but I can already tell you it's not on the front pages now, but it'll be in use for the next 10 years or so, if you think back on 3 Mile Island and Chernobyl and so forth. I wanted to give you kind of an initial assessment or a glimpse of, in about 45 slides, just a snapshot of what's been happening. All right, so this is when it started, 2:46 in the afternoon. I think it was I believe it was a Thursday afternoon in Japan. So it was Wednesday, our time in the U.S. All right, just some quick metrics so that you remember. A 9.0 quake was originally 8.9, but then later corrected to change to 9.0. About a 14-meter tsunami wave, and it's not like it's not like a surf wave. It's actually a solid wall, 14 meters high, that was moving toward land. Okay, so and then the Fukushima nuclear power plants. There are 6 units there on the site there, right on the ocean. They actually survived the quake and the tsunami, but in a damaged state. Okay, so that damaged state is really the beginning of the problems that they had. Okay, I think that makes sense. So it wasn't like some of the housing that was, all the other structures, the wooden structures especially, that were just leveled. And the buildings were still, the turbine building, the reactor building, and many of the larger buildings were still standing. Okay. All right, here's just the things that there's a million images and video clips, and there's a new one that's coming out each week. Somebody, survivors, is now finally able to download images that they captured. It's really the first global disaster that had so much web coverage, right, on YouTube and everything. It's just been a tremendous amount of information. So this is the Sendai airport. It's in one of the prefectures. And it was a very flat area, of course, because of the airport. And you could see the water just coming in. And there were actually some jets, Boeing and probably some Airbus, that were actually parked on the tarmac there, but they got swept away. Okay. Here's a refinery fire in Chiba, just a little bit further south. But yeah, this after the quake and the tsunami, this got set on fire right away. Yeah.
Professor, what is the EDNT?
Yeah, let me go back. Yeah, I knew somebody would ask. And so I would tell you I'll explain it a little bit later, but D is for distribution, E is for energy, and N is for number. I'll talk about how you might possibly remember or look at complex issues as well. So this is EDNT. Here's the next picture, airplanes and cars. This was actually at the airport that you saw this. There was a video that had, you could see just the planes and the cars just going right by where they were filming in one of the buildings that survived. And most of it is, you see in color, you see just a lot of lumber, timber, right? All this brown that you see. Right, and then the quake. There's actually the wave that's coming in. Typical pictures of post-earthquake. You know, the pavement buckling and liquefying. This one was a kind of a neat picture that had this oriental kind of a gate, and then all the debris flowing through there. Right? All right. So, and here's our metrics. About 15,000 dead. This is still on counting. About 10,000 missing. About 150,000 uprooted. Actually, more than that. Actually, so the people that had to evacuate not only because of the earthquake but the tsunami, and then in addition, the nuclear power plant accident. There's 60 days. I had that on the very first slide. 60. We're now at 60 days. Today's the 10th. It's already the 11th in Japan. Their future is completely undetermined right now. Okay. All right, how does one process so much information? I mean, there's been just a deluge of information and news reports and mass media coverage is, it's just been tremendous. This TLEDN, if you want to look at complex issues or complex phenomena or problems, sometimes I think that we tend to talk apples and oranges, and if you can accept that we should talk in terms of time scales, line scales, energy scales, distribution scales, and number scales. I think time scales are pretty obvious. How many minutes was the earthquake? We're at 60 days now post earthquake. That's a time scale. Okay. Length scales are how many miles between the power plant and the nearest populated city. That's a length. Or L squared, or L times L is an area. L times L is a volume. So these are kind of length scale arguments. Energy scales are really about loss of electrical power. How much energy did the earthquake have, and so forth. So distribution about where are the zones of contamination. Those are distributed. It's not equally distributed over the whole area around the reactor. Okay? So, and number scales are really about things that you can count, and the most important one is about dollars. Okay. So here's just some metrics. So TLEDN, time scales. The initial quake was about 6 minutes. It shook for about 6 minutes continuously. I saw some reports that were about 8 minutes. I've been in a few quakes, and that's a long time. Most quakes are under a minute or so typically, right? And then the population the country is still recovering 60 days after. We're still. The epicenter was about 70 kilometers, 45 miles east of the coast. If you look at the map of Honshu, which is the main island, the banana-shaped kind of island, it's about half the area was affected. Okay, so half the landmass there. D is the distribution all along the northeast coast of Japan. Felt the earthquake and the ripples. And then, as far as another distribution, the whole supply chain of the whole Japanese economy was disrupted. Okay, so that's what I meant by disturbed or disrupted. All the train route lines that go all the way from the north to the south, that was cut. Okay, and they just established that about, what was it? I think it was about 50 days later. Now finally you're able to go from the very tip of Japan all the way down to the south. In terms of energy scales, estimates, I guess if you're a geophysicist and you specialize in earthquakes, 9,000 gigatons of TNT equivalent. That's the amount of energy. About 600 million times the bomb that was dropped in Hiroshima. That's how much energy that was released. Okay, so that's the energy scale we're talking about. It's tremendously large. And then the number scale, I guess, like I said, 15,000 deaths, 5,000 injured, 10,000 missing, 125,000 homes destroyed. So far, $30 billion US dollars in insured losses. And the Bank of Japan, BOJ, just infused $183 billion to keep the yen stabilized. Okay, so those are the number scales. Those are these are kind of metrics that tell you quickly what the magnitude of the damage was. All right, where it happened, the prefecture are the states, to the left, to the right. I guess there are about let me see, well, 6 or 7 prefectures. Three prefectures directly. The power plant is right there. Okay, and then you see a magnified map. There's a 12-kilometer range and a 19 miles and 12-mile range. And I think what's really part of what saved Japan, because it's an island, is that half the area is in the ocean, right? That you don't have a landmass all the way around around the perimeter. Okay, and then the Daiichi plant. There are 2 sites. There are 4 units here. These are numbered. You have to remember it goes backwards: 4, 3, 2, 1, and then 5 and 6 are a little bit on the same side, but a little bit further north. Okay, and there's kind of a breakwater kind of thing structure here to break the waves, and there's this little port area. And you see a lot of little details. The longish rectangular shape is the turbine building, and the reactor building are these bolded square structures here. And you see a lot of details. And this actually impacts all these little structures and pipes and tanks and so forth that were on the ocean front. They were the first to be damaged and made inoperable by the tsunami. Right? Okay, so this one is about length scales. All right, mass media had a field day, right? There's nothing better than a crisis for mass media. Fox and CNN and so forth, right? I think even Nancy Grace was talking about the earthquake and the tsunami. So they said, I heard a news story that it would have been better if Godzilla came out of the sea and then destroyed the nuclear power plants himself. But so there was a kind of a character, a cartoon that said the news would have been just a little bit better if Godzilla had appeared. But so this is just to show that. Just to show that mass media had something to report for at least 2 solid weeks, if not a whole month, right? All right, as far as the plant, before and after the quake, I wanted to show you. Here's the bird's eye view of the plant. Like I said, this is in German from Der Spiegel. They had some really nice images, so I took those. There's unit 4, 3, 2, 1, and there's 5 and 6 here, okay? So you can see that these are the turbine buildings. You can see that it's right on the ocean. Okay. All right, here are some specs on the reactor. As nuclear engineers, we like to look at specs. The reactors are these 6 units. They're boiling water reactors, the BWR. We love to use abbreviations as nuclear engineers. They're Mark I type, so this is kind of looking at a car spec, really. These are the dates when they were constructed, when they first went critical. I won't talk too much about that, but then when they first went into operation. So, the first Unit 1 was construction started in 1967. So these are, I think, a bad analogy about reactors is that if you see a date like 1967, it's like a 67 car. So if you think about 67 Mustang, could you still be driving if you take care of it, could you still be driving a 67 Mustang today? Yes. But would it have anti-skid brakes? Would it have 6 airbags inside the car? No. So, if you bought a new Mustang with the anti-skid brakes, 6 airbags, and you have a 67 Mustang as well, they're both cars, but the relative safety of those systems are really different. Okay. So that's that. So I think they're vintage, 70s, 60s, and 70s. And then this is the thermal power, this column. And then the electrical power, the conversion is about 33%, going from thermal to electrical. And this is the design peak ground acceleration in G's, at which the reactor automatically shuts down. So when you have movement, a lot of movement, at least for, and a little bit different for this first unit, maybe because it's an older unit already at 0.18 G, lateral ground movement, it automatic shutdown system initiates. Okay, and all the reactors actually that were operating at the time of the earthquake shut down, and these are all 0.45. The two that were planned, they were just canceled because of the earthquake. They're about to start construction early next year. That's not going to happen. Actually, yeah, it says they were canceled in April, just last month. Here are the constructors. The reactor fuel, how much nuclear fuel is actually in the reactor in terms of assemblies. I'll show you a picture of an assembly a little later. This became an important factor because after they shut down, they're still producing what's called decay heat. It's really like if you've done some ironing. If you turn off the electricity to your iron, is it still hot? Yes, it is. And how long does it remain hot? That's the kind of leftover, the decay heat. So it's producing heat even after you turn off the reactor. It's producing heat for quite a long time. Okay. So how many fuel assemblies that are in decay heat is an important metric. And then you usually put in fresh fuel in a reactor every 18 to 24 months and take out 1/3 of the core and then put that in what's called the spent fuel pool. And they have to cool a certain amount before you can actually take them out of that building. So there's a co-located spent fuel pool at the reactor, and these are the number of fuel assemblies. The Unit 4 actually was undergoing fuel refueling, so they had taken the entire core assembly out to the reactor and put it in the spent fuel pool. That's why this number is so big. Okay. And then the type of fuel LEUs, just lower enrichment uranium. Fresh fuel, they had a supply of 204 here, and then all these other numbers here. So the only other thing is that if they eventually, when they take the fuel out of the spent fuel pool, they have what's called a central spent fuel pool, and that actually had, at the time of the accident, 6,375 fuel assemblies in it. So when they run out, when these have sufficiently cooled, then they take it to a central site. Okay, it's essentially a 50-foot swimming pool, and they have these assemblies that are still cooling beyond the period that they spend here in the spent fuel pool. All right, here's a picture. I couldn't quite get kind of the identical perspective, but this is when before the quake, kind of looking at the same view. This is actually the picture. I think it's a little bit further down, kind of down this street here, but when the water was coming in. Okay, they have these embankments, or I'm not quite sure how high they are, but they're certainly more than 15 meters high. Okay, and the water came just rushing in, and so it really just inundated and just flooded everything that was through any opening that they could find in the turbine building, and the reactor building, and all the offices and so forth. All right, here's the Mark I GE boiling water reactor. This is what it looks like. The details are not too important, except I'll just point out a few things. It has this thing called the suppression pool or wet well. It's a donut. I'll show you. Let me see. I'll just go to the next slide and come back. Here's a picture of one that's under construction. This is the this toroidal suppression pool or wet well, and you see these legs going out. And this is actually what's called the Reactor Dome. And you saw, this is actually in color. It's at the Fukushima plant, it's been painted yellow. Okay, so here's the reactor vessel. Let's go back. So that dome is this cap here, this yellow cap. Okay, you saw this in some of the post explosion pictures. You saw this large, very large structure that was yellow. That's this dome here. And here's the suppression pool again. This is the spent fuel pool, or right here. I guess this is the spent fuel pool. that has, you take the fuel out of the reactor. This is the reactor itself. You take it out, and it first cools down in the spent fuel pool. Okay, so this is about 50 feet. They sit in about 30 feet of water. And then the only other structure that's you'll see in some of the other pictures is this overhead crane. Here it's orange, but in the actual picture they painted it green. So this much, all this underneath this level is all concrete, and then they just have what's called a confinement building. It's just a weather proofing building. It's not, everything that's concrete is what's considered reactor grade, and considered part of the reactor building and the reactor structure itself. But everything above that is kind of more for weathering. Okay, and it turns out this became a factor in the accident. All right, here's again under construction. Oh, incidentally, this torus here, it's as the radius is something on the order of it's as big as a 747. You could stand inside it, and it's a huge dome structure. A huge fuselage type scale. Okay, so that's the length scale thing. All right, here's the fuel assembly. Here's a spent fuel pool. It doesn't look so deep because the water is really clean. Okay, but this is probably sitting. You can see kind of the free surface here with this fuel handling tool. That's in this area here. And this is already sitting from the surface of the top of the fuel assembly to the top of the pool. The free surface is about 30 feet of water. Okay, so you get quite a lensing effect. You can see it quite enlarged. So this thing is a good. This says what, 13 meters there. It's really quite big. And then inside here you have these fuel rods and inside these fuel rods, so there's an array of usually 14 by 14, 15 by 15, 17 by 17 fuel rods. And then inside those it's really just a pin, a hollow pin. They have these fuel pellets. Okay, so this is what's called a subassembly, and this is what I had in the table in terms of the number of subassemblies. Okay. All right. The only reason I put this figure is this one showed the relative elevation of the reactor building in the turbine building, which includes the condenser, and then the channels that go into the sea. Okay, this is the ocean side, this is the building side. So in terms of those pictures, you see this large structure, the turbine building, and the reactor building here. Okay, and what's important to note is that there's water inside the reactor, of course, and there's a pathway from inside the reactor all the way out to the ocean. That's what's one of the issues, that there's a pathway in terms of water or channels. When they become flooded, there's a way for the contamination to get out into the sea, and this is exactly what happened. Okay, so I think the nuclear industry is learning about some of the things that we really can't have channels and volumes that are linked so that they can go directly into the ocean. Okay, and what happens when you have when your basement floods? When you have heavy rains, your basement floods, right? So that's not any different here. What flooded? The basement of the turbine building. So there was a news report that 3 workers, subcontractors for Tokyo Electric Power Company, got exposed. The interesting organizational or the institutional dynamics, these workers were told by TEPCO, they were a subcontractor of TEPCO, Tokyo Electric Power Company. They were told that before they went in, that the floor might be wet, but you didn't necessarily need to wear boots. So 2 of the 3 did not wear boots, and they went in to the basement, and there was 15 centimeters of water. So they got completely soaked, and they got exposure. So the other thing was they were given radiation badges, and it was set to, I think it was 20 millisieverts. We'll talk about radiation units. Already when they approached the building, the alarm went off. And human nature says, hey, that can't be right. I'm not even in the building. So they didn't believe it, and they said, like hitting the snooze button. They ignored it, and they kept going. So it's kind of curious what, human nature, how that impacts the behavior of people. So, so that's that. Time zero start of the accident energy scales. We go from at operating power, 2,400 megawatt thermal in terms of heat, right? Heat energy or thermal energy. About 10% of that is upon shutdown. Immediately after shutdown, you go to about 10% level, about 240 megawatts thermal. Here's the decay heat. Just in terms of time scales, at 0.1 seconds you go with this unit 3 and unit 4. They have different power ratings, about 139 megawatts. We're at somewhere, we're beyond 11 days, but we're not quite to 116 days. We're about halfway to 116 days. We're still not below a megawatt in terms of decay heat. Okay, so remember what I said about the iron? 116 days later, the iron or the stored heat of it's still warm, and it's still, there's not much heat, but it's still there's, unless you cool it, there's still enough heat to melt metal. Okay. So in this case, so we won't get down to, what is it? We're at 60 days, another 2 months. We'll finally get below a megawatt of power. Okay. And then for this other unit 4, well, it's going to be a little even beyond the 116 days. Okay. All right. Everybody has heard about explosions. We used a zirconium-based what's called a cladding material. I said there's a fuel pin, and inside are the fuel pellets. This pin is made of what's called zircaloy. It contains zirconium. Zirconium reacts with water, liquid or steam at high temperatures, and it produces hydrogen, directly hydrogen gas, and then zirconium oxide. Hydrogen, of course, oxidizes in air. The lower explosive limit for hydrogen in air is at 4%, it'll already explode. Okay? So, hydrogen in relative comparison to TNT, energy basis of TNT explosion about 4.5 megajoules per kilogram. Look at the explosive energy of hydrogen. It's about about what is that? About 25 times, 120 megajoules per kilogram. So we had hydrogen explosion. Well, most likely a hydrogen explosion at the 3 Mile Island accident in '79, and then 30 years later, we had at Fukushima we had a multiple number of hydrogen explosions. Okay, so here's one of the explosions. I mean, you can see in terms of this is about 50 feet in length scale. You can see how big that explosion, how much energy that it dispersed. At least twice the height. Okay, and you saw that from the comparison of TNT versus hydrogen explosion, how much energy that it has. So you wonder why we still use zircaloy or zirconium-based cladding material in the nuclear industry. Okay, so we have. That's one of the lessons learned, I think, that we haven't learned the lesson. All right, so here are these kind of before and after. This is the before, the aerial photos of the 4 units, 4, 3, 2, 1. This is the ocean side, and you can see the damage, corresponding damage state. This is unit 3. Unit 4 is here. These are these drone images that were taken. That gave us good high resolution images. All right, here's a kind of a side. So you saw this side perspective. You saw this picture of this structure, what I call a weather confinement building that's above this reactor dome. It had these kind of sky blue panels with these cloud patterns. That was completely blown out. There's one picture. Here's the embankment that you saw in one of the previous pictures during the tsunami. Here's the kind of the transition. So you have this tremendous amount of decay heat, and you got to provide decay heat cooling. And with light water-based reactors, then you have to cool. You have to extract the heat, so you have to pump water. Okay, so. I think there's this And the height of the building, that height there is about 50 feet to the top of the building. So this Putzmeister, the super pumper, was used to pump concrete, and they could pump water as well. We had to fly out one out of the U.S. using a Russian transporter that could carry it. And because Japan didn't have this pump, this super pumper, this Putzmeister, that had this extended arm that could go all the way to the top of 50 feet and inject water into the spent fuel pool, and then also into the reactor. All right, I think there are more units going from the U.S. to Japan. All right, so they put a camera on one of these Putzmeister super pumpers to get a close-up look, because the radiation levels were really very high after the explosion. You can see the extent of the damage. This is in between, I think, probably building 3 and 4. This is the side wall of this confinement building with this blue and cloud patterns. Here's a little bit of the green. You saw that I talked about the crane that was orange before in the schematic. In this plan, it's actually green. Okay. One of the stupid things that I noticed in looking at all these pictures is that there's a lot of gray. So, and what you can identify are things that are in color. Yellow or green, you know what it is, okay? Here's the other one. Here's another close-up. This is the crane over the spent fuel pool. Like I said, it was in orange in the other image. And there's a lot of gray, and you see a lot of bent shapes, but you really don't know. It's hard to say what it really is. Have you noticed in some buildings, when you go to the basement, you see all the utilities in the building? Cold water is blue, painted blue pipes, and then the hot water is red. If you you think there's not much engineering in that. I mean, it's kind of low level, but if you had color-coded some of these components, and if you take, after an accident, if you take the image, you would know what it is. Okay? So that's a really a simple lessons learned, that we need to really color code these major components. All right, here's not the super pumper, but they tried with a fire engine hose, and it was hard to get enough water into on top and then coming down into the building. You know that you're spraying water, but you don't know where it's going. You don't know if it's reaching the destination, intended destination. And it's one of the problems. Here's the image. This is a little bit more of a schematic. This conduit that they talked about, called the trench, was for electrical cabling, but it probably got flooded when the tsunami came in, and it served as a path for all the water that we were pumping in. That had to flow somewhere, and eventually found its way from the reactor building into the turbine building, and then into this electrical conduit U-tube-shaped trench. And this was going out into the ocean. Okay, so if you have a path, then there's, for water, for any liquid, there's a way to get from one place to the other. Okay. Yeah. So the other thing is that you cannot, looks like, indiscreetly be pouring water or injecting water. Eventually, these volumes fill up. Then they're all contaminated, and TEPCO has spent weeks moving one filled tank into another empty tank, so that they could move, this was filled, they had to empty this, then they had to empty the condenser. Everything is contaminated. They had to move, this volume analysis of empty tanks and filled tanks, and that all takes time to do. Okay. All right, the plant status, kind of most recent. This is already 4 years old. There's a daily update of press releases and so forth. Just kind of highlighting, they've now just entered the Unit 1, and they're installing some air filters, because there's too much. There was an early iRobot video clip, and they went into Unit 3 and 4 at the ground floor, and it was like it was such a sauna there, 99% humidity and high temperature. They had a radiation detector, and you could not even see the LED display because there was so much humidity. It was like trying to read on a silvery LED display inside a sauna. You couldn't see it. Okay, so they said, oh, we need to have a dehumidifier, take the humidity out of the air. They've just installed a number of kind of dehumidifier with a particulate filter to take some of the airborne radioactive moisture out of the air. Those units look pretty small. I'm not sure that's going to have much influence because, you may be extracting the humidity, but there must be another source of humidity where all that humidity is being generated. So, but that's what they're doing because they need to know. They definitely need to put people inside in the recovery process, people inside the units. So, since you lost offsite power from the generators due to the tsunami, actually the diesel tanks survived, and the backup diesel generators were in concrete pits. They survived the earthquake, but they didn't survive the tsunami because that pit was underground and it got flooded. Okay, and then the connection of the diesel fuel lines from the tanks to the diesel generators were cut. Okay, so you had no hope of backup diesel power. They operated only for about 45 minutes between the end of the first major 9.0 quake and before the tsunami hit the coast. There was about a 45-minute gap there. Okay, so they operated for about 45 minutes, but then they stopped. If you don't have the backup generators, you don't have the capacity to take the decay heat cooling. So then you also have what you call a loss of heat sink. You don't have you've lost your capacity to take care of the decay heat. So 60 days, we're having to do something that we never had any plans to do. We're going to install improvised heat exchangers to still take away the decay heat. So that's this first bullet. As a result of contaminations, there was kind of the economic impact was that Japan was not able to export a lot of its products. I had a guy from Chicago call me. He worked for Japanese companies. They were getting products sent from Japan, from south of Japan. And his customers were worried that whatever components they got would be contaminated. He said, what kind of radiation detector can I buy to make sure that my customers are not worried? So it was not only vegetables and meat and so forth, and they're now just trying to remove the restrictions on exports. Already 2,000 workers at the Daiji site from the Tokyo Electric Power Company. You can see the plant workforce is now about about 1,000. The problem with this is that once you reach your annual limit for radiation exposure, you're done for the year. And that could happen if you go in a high radiation area. You could be done in about 40 minutes, or I think Chernobyl after that accident, each worker that got to do part of the recovery effort, 40 seconds. And that was it, and they had to go run back. So how much work can you do in 40 seconds? Okay, you have to ask maybe a graduate student how much work you can do in 40 seconds. Okay, but so this is when you have radiation exposure limits. It really has a tremendous impact on the cleanup workforce. Okay, all right. Radiation levels continue to go down, but there's still a significant. They're high enough so that you could, if you spend a significant amount of time, you could go beyond your annual exposure. All right. There's another nuclear power plant that's actually sitting at the juncture of two faults. Actually, it should say Hamaoka, and now the Prime Minister has said you will not operate that reactor, and that's been in the news the last few days. All right, radiation basics. I know it's been confusing that we have this thing about millisieverts and becquerels. Okay, here's my bad analogy of the day. the amount of fuel or the mass of the firewood we measure in becquerels or curies. These are the two equivalent units that we, well, unfortunately they were, they're named for Nobel Prize winners, Becquerel and Madame Curie. They're the same unit in terms of how much the mass of firewood or the source of radiation, how much radioactive source material do you have? That's in becquerels and curies, okay? And 1 becquerel is 1 disintegration per second of a radioactive material. The heat, or the heat that one feels from the firewood is the exposure, okay? So exposure is measured in sieverts per unit time. Sieverts is a very large unit, so you usually express them in microsieverts per hour or millisieverts per hour, and millisieverts per hour is 1,000 times bigger than a microsievert, okay? So the exposure, you can have radioactive material, but if you don't have a human being around it, then you're not talking about exposure. You're just talking about the mass, really, or the amount of radioactivity that's there. So that's becquerels and curies. The exposure itself is about millisieverts. All right, here's the radiation day in life. We're living in a radioactive environment. 1 CT scan is 6,900 microsieverts per unit time. You're already, I think the average in the United States is I think about 620. I think about 620 microsieverts. If you get 1 CT scan, you're getting a big chunk of radiation there. Okay. All right. Here's the relative radiation levels. You know that radiation levels are very different in different locations. Denver, if you live in Denver, you're getting a lot more. You're a higher altitude. If you're a mile-high city, then you're also getting that much more radiation from outer space. There are locations where people live that you get a lot of exposure. This orange line here is the what was measured. I think probably does it say in Tokyo? Probably over the days. So you can see that here's where is it? The CT scan is right over here. Yeah. And you have you can see that there are cities that have a high radiation background, what's called natural radiation levels. And actually, there was one that was, smoking 1.5 packs a day, you're way up here. Okay? So, radiation exposure is not good. I mean, just as you can say that smoking 1.5 packs a day is not good. Risk is relative, right? It's based on whether you perceive as an individual whether it's beneficial to you. If you cannot give up 1.5 packs a day, the benefit is overwhelming the perception of risk. Okay, so same with riding a motorcycle without a helmet. The benefit of that nice feeling of the wind blowing through your hair, that's benefit, and I'm willing to do that and not wear a helmet. Right?
Curious with some of that alpha and some of this gamma.
Yeah, there's 3 types of radiation. Well, there's 4 types: gamma rays, or photons, so no mass. Beta and alpha have mass. Beta is essentially electron mass. Alpha is helium atom mass, and then you have neutrons. Betas and alphas with very little shielding, you can block that and prevent being exposed to that. Neutrons have no charge, so they go through almost all materials. So neutrons can do a lot of damage. So you have to, and then gamma rays are typically what's emitted by from the fission, what are called fission products. You take the uranium and you split it, fission it into 2. And those are fission fragments or fission particles. Those give off intense levels of gamma rays, typically, and those are dangerous. Okay, so neutrons are by far the most dangerous, but I'm not too worried about that we have neutrons that are flying around at Fukushima, but we do have intense gamma rays, and that's a little bit worse. And you have some betas and alphas, but the shielding or protecting yourself from alphas and betas are relatively easy. Okay, the gammas you get some attenuation from having layers, but sometimes you have to have quite a bit of shielding, lead shielding, for example. Okay. All right, here's the kind of the ground-based and the aerial map of the radiation. So this is what I was saying about the distribution, is that depending on the wind direction and how the which way the wind blows and how the solid particulates were deposited on the ground, the radiation levels are very different. So you see this distribution. It's not like it goes everywhere in all directions equally. Okay. So there are some towns along this yellow streak here that, the whole village is contaminated, highly contaminated, and others, if you live right here, there's no exposure here at all. Okay. So those people who were evacuated within this radius, the evacuation zone, let's say there's 20, 30, and 50. These people will be able to, in these villages and towns, be able to go back. But if you live in this streak, you're not going to be able to go back home for a very long time, until they decontaminate that little village. And even with one little village, if you had to think of all the surface area in Moscow, there's a heck of a lot of surface area, right? So it's not only about rooftops, it's about the sides and everything, right? So here are the radiation levels, and this data really does help you in planning the remediation of the cleanup effort. All right, contamination. 10 to 1. These are rice paddies. The price of rice in Japan, because it's heavily subsidized, it's 10 times the world average price. The farmers in Japan, the rice farmers in Japan are very good lobbyists. And over 50 years, they've convinced the government that they need 10 times the subsidy to produce the rice. Okay, so now it's really a cash crop. Okay, so now these farmers that are in these contaminated areas are told in the spring, right now, you cannot plant rice because this is all contaminated. So talk about loss of income. They don't even know when, in how many years from now they'll be able to plant rice. So they don't have any income. Same with, but less so with vegetable farmers. A lot of the vegetable farms, spinach, different types of vegetables have different uptakes on radioactivity. Spinach and kind of those green vegetables were detected first in terms of radioactive content. And then sushi or sashimi, fish, you know that the fish has been contaminated as well. Okay, so this is a problem because the Japanese like to eat rice, like to eat vegetables, and like to eat fish. And now you're saying you can't eat any of that. You're going to have to switch to meat and potatoes, right? Maybe Idaho potatoes. You can't take a country that has a traditional eating habit and then they say, hey, you can't do that. You're going to have to do, that's like saying you take, meat and potatoes person and say, oh, you're going to have to eat raw fish from tomorrow, right? So it's quite a cultural change. So this has quite an impact. All right, post-accident management, recovery, restoration. Here's my projection. We haven't seen this in the headlines. I think it'll be coming up in the next week, 2 weeks. Eventually, these figures will come up. At least 10 years. Whoops. Cleanup. I think maybe 20. I'm kind of being on the low side. At least $10 billion, maybe $20 billion, just for the cleanup of the reactor site. So that's the number scale. At least 10,000 workers. That's the number scale again. Because you have 1,000 workers, if they reach their radiation annual limit, you can't use them anymore. So this is really a problem. So I think this is a low number. I think it may take 50,000 workers. Do they have the 50,000 workers to do the cleanup? I'm not sure. Okay. All right. Here's the comparison with Chernobyl. It's we're now the Fukushima accident. There's this international nuclear event scale. Both Fukushima and Chernobyl are at the very top major accident. This is the scale. It's really, it's kind of silly. I think it's kind of silly, but it really has nothing to do with the actual the reality of and the significance of the accident itself. It's just okay, if you have to give it a scale, okay, you can give it a scale. Okay, here's just because people have, when you hear nuclear accident, you first think TMI, Chernobyl, and now Fukushima has joined that group. Here's Chernobyl, an image. Here's an image from one of the inundated villages. Here's this is probably a concrete structure that withstood the tsunami and the quake. This is not Fukushima. This is from Hiroshima. Okay, but you look at in terms of the devastation and how it flattened everything. It's if you look, this is quite a different type of event, but just in terms of the devastation that you see, it looks very similar. Okay, just as a comparison. All right, did we melt the core? Yes, we did. Probably 3 units. We probably partially melted the core. We will not know the extent until about 2000. I predict from 2015 to 2016. This is from Wikipedia, the 3 Mile Island accident. There's a diagram of how this part is intact. Everything else above it we melted at 3 Mile Island. These are some of the actual first images. I say it's about 2015 or 16. I remember I was a graduate student when I first saw the accident was in '79. I first saw the images. We had a special seminar, and we were showing the first images of inside the core. I think it was 85 or 86, so 6 to 7 years afterwards. Maybe we can do a little bit better this time, but I think at the earliest 2015 or 2016 before we actually get a camera into the core to look at the full extent of damage. And it looks like some deep, seawater. It's just spaghetti inside. It's really a mess. So I think it's going to probably look very similar. Okay, but kind of stay tuned until 2015-16. All right, accident management in Japanese style. There's TEPCO, the Prime Minister's Office, Nuclear Incident and Safety, Nuclear Industrial Safety Agency, Nuclear Safety Commission, and then of course the IAEA, International Atomic Energy Agency. The accident management's been pretty dynamic. This is the CEO of TEPCO. This is the chairman of NISA. Here's Prime Minister Khan. There's his chief cabinet speaker. This is the Secretary General of the IAEA, who also happens to be Japanese. This is Professor Madarame from University of Tokyo. He's the head of the Nuclear Safety Commission. Everybody, for a good month, had their own press conferences. Then 30 days later, they decided we would have a joint press conference. Because throughout the day, they had press conferences at different times. People were saying different things. Okay. All right, the art of bowing. If you've seen bowing, this is a large part of Japanese culture. This metric here, this number scale, 23:1, is the ratio of how many lawyers we have in the U.S. compared to how many lawyers we have in Japan. Okay, and this is to show that in the United States we have a society that's based on litigation, and Japan is 1/23 that. We don't have, Japanese society is largely not a society based on litigation. So if you have some accident, you would think in the United States you're going to have a lot of lawsuits, right? Yeah, Corey?
When you say the ratio is 23:1, are those relative ratios?
Yeah, I think I looked it up in a Japanese almanac and then an American almanac to see how many practicing lawyers there were in each country. I think I did this. I looked at this. This may be a little bit old. I think it was about 10 years ago that I looked this up. Okay. So there's a lot of significance in the bowing, and this is kind of a bit of making a little bit of fun, but the angle or how far you bow has some meaning, and about the seniority. Clearly, in the Japanese society hierarchy, the Japanese government, in terms of institutions, the Japanese government is at the top. certainly Tokyo Electric Power Company, they think that they're just one level below the government, because TEPCO is a company that's as large as Toyota. In some years, they made more profit than Toyota. Okay, so they consider themselves. They have 33% of the electricity market in Japan, and where the electricity costs about 3 times that of the United States per kilowatt hour. You know, they have a lot of money. Okay, so we'll see what happens. Bowing is to, in some manner, I might say, to offset lawsuits. We'll see what happens. Okay. All right, lessons learned, technical and non-technical. We've just submitted an article it's going to be published. Let me see. Let me talk a little bit, a side point. Engineer for safety. Reactors are, if you plot the probability and the consequence of an accident, you have, you know, some high probability and with low consequence. You can have small accidents like a flat tire that has relatively small consequences. And then you have things that have very low consequence or low probability but high consequence. It's like what is the probability that you were driving on the freeway and you had all 4 tires blow out at the same time? That's low probability but high consequence. You would definitely lose control of your car. Okay, and you know, your health could be, you could die in such an accident scenario. Okay, but one flat tire you could probably manage. Okay, so reactors are designed and engineered for safety to cover this area: the anticipated, the flat tire, you know, an electrical fault or something, and then these low probability events, these unforeseen events, we really don't engineer for that, because, you know, they're a low probability. Why spend the time and invest the money and time to design for this area? So this area here is based on what we call system resiliency, and we don't have very much system resiliency engineering in this in all over the world. Okay, you don't. And resiliency is really that's how well is the structure built that it can manage in some manner to sustain the damage and operate, serve its function to, in a transition mode down to, if you have a car, for example, to slow down and stop on the side of the road. Okay. All right. So system resiliency. I'll take the ABS as an example. We have that as a safety system in a car. Like I said, if you were driving on the freeway and you had a blowout in one tire, can you drive on 3 wheels? Yes, you can. If you immediately manage the accident, the incident, slow down, you know how fast can you drive. If you were going 60 miles an hour, you had a blowout, you managed to keep the car in control, how far, you know, how quickly would you have to slow down, and what's the speed at which you can drive the car? Maybe 15 miles an hour on the side of the road until you get to the exit, right? So that's system resiliency. The car is built well enough so that you have input through the steering wheel and the brake that it's able to manage this blowout in one tire, driving first initially before the accident at 60 miles an hour or 75 miles an hour. Of course, you could, if you don't manage the wheel right away, you could go right off the road and flip the car. Okay, so there are different accident scenarios. All right. So, technical lessons learned. The reactors were designed to withstand a 7.8 quake. It underwent a 9.0 quake. Did it withstand the accident, that 9.0 quake? I would say it's yes. Okay. Multiple reactors, old reactors shut down automatically. It did. Like I said, the 60s and 70 vintage reactor. Multiple older reactors withstand a tsunami only partially. You cannot get through that tsunami, such as the one that we experienced, without some damage. Okay, I think that's common sense. The cladding, fuel react with water at higher temperatures and generate hydrogen and explode. Yes, as we also observed at TMI, hydrogen can accumulate and explode. So we haven't really made any improvement there. Since nuclear power is dangerous, shouldn't we shut down all 100 reactors in the U.S. and 50 in Japan that we have now? 100 reactors in the U.S. generating 20% of the capacity means if we shut down all 100 reactors, that means we lose essentially 20% of our electricity. One workday a week, we would not have nuclear-generated electricity. And I would say, I would argue that that's probably about 20% of the economy. Okay, so can we take a 20% hit on nuclear-generated electricity? We can't, not today, okay? So can we reduce the number of reactors, but we're not going to go from 100 to 0. Okay, and the same with Japan. Japan is 35% nuclear-generated electricity. They cannot go without. They don't have any other, they don't have shale. They don't have hydro. Well, they do have hydro, but it's all already tapped out, okay? So Japan, without a country without resources, energy resources, they really now are forced to make the decision, how many reactors can they have as part of their national energy mix, okay? All right. We just, in the May issue of Nuclear Exchange, we just had about 20 technical lessons learned published. And I'm just giving you a couple of these. Here's the one that's kind of a no-brainer that I said we need to color code the major components so that if you have an accident and you take, the first thing you want to do is take images. If everything gets grayscale, it's hard to identify what's still intact as opposed to what's broken. Okay, so this is kind of a stupid one, but it's actually important. Operational, post-tsunami and post-quake, there was a lot of debris on very narrow roads in Japan. Those large trucks could not get to the plant. All right, so you got to clear the debris. You got to have roads wide enough for first responders to get to the plant. All right, and then one thing that was clearly lacking is that you have a plant on the ocean front, but did you see a lot of motorboats and jet skis, and there was almost nothing coming with direct access from the water side to the plant. Okay, so that I thought, oh, this is kind of strange that we don't have a first response team that can come with dinghies or that can go access the plant right away. Okay, everything was land-based, so that thinking needs to change. And then, yeah, I think what we should do, Japan, in terms of the cleanup, if it's going to cost 20 billion, 50 billion, a 10-year effort, I don't think the Japanese government's going to be able to pay that. So one idea I had was, why don't we designate the Fukushima site as an international cleanup site? There are clearly people, the vendors, Hitachi, Toshiba, Westinghouse, GE, all these big, Bechtel, Babcock and Wilcox, all these multinationals, they're interested in getting the contract to do the cleanup. They're looking at the dollars, right? They want that $10 billion contract. Well, why don't we make it an international cleanup site so that you get every company who wants to go there gets the experience to do that, okay? So that way, it's a kind of a cost-shared idea, right? All right, and like I said, we really need to spend some R&D money on getting away from zircaloy or zirconium-based cladding. And these double design basis accidents. So can you have loss of offsite power, loss of heat sink? Can you have actually the quake and the tsunami usually go together, right? And we build the plant so that it cannot have a severe accident. The probability of a severe accident where you melt the fuel, as designed, is one chance in like 10 million or 100 million. Okay, that probability is very small. But where's that plant is not sitting, elevated up in the air. It's sitting on the ground. And in Tokyo, if you look at the incidence of large earthquakes, 7.0 or larger, in geological time, they've had like 5 or 6 in the last 500 years in recorded history, okay? So that 5 in 500 years, it says that the probability of a large accident followed by a tsunami is more like 1 in 100. Even though you build the reactor to be 1 in 100 million that you would have a severe accident, the land that it's sitting on has a much higher probability for something happening, okay? So we need to rethink that process. All right, we have some posters in the back. We, in one of my, we have two students here, Corey and Brian. We made some posters. We split up. We started with March 11th, and each group did about 6 days. Then we have an overall poster. I think we prepared about 4 journal papers. We're about ready to submit that. Most of my images and so forth were all through all these news sources, and it just keeps going. I'm still looking at the news releases and so forth, the news reports, pretty much on a daily basis. So, thank you very much. I think that's the last slide. Yeah. So I'll be happy to answer any questions or have a look at the posters if you like. Corey, Brian, you don't have any questions?
Learn about it all class.
Yeah, they learned quite a bit. So this is going to be kind of a standard classic accident. As a nuclear engineering student, you learn about TMI and Chernobyl. This will be the 3rd classic study case. Yes?
Actually, I had a question. You were talking about getting away from the zircon-based cladding. What else would you use, or is there something else in use already that they could?
No, there's not. There's some history of aluminum-based cladding. There's a great aluminum 6061 that some research reactors at university, smaller reactors, use, that's been underwater for 30 years with no corrosion or pitting or anything. It's really remarkably well adapted. But aluminum has a low melting temperature, so you cannot use aluminum as a cladding for high power reactors like the ones we have. The only other thing that's kind of on the horizon is maybe silicon carbide, ceramics. But ceramics are typically very brittle, right? So they can't withstand quick temperature changes, or something that's 1100 degrees and then you want to go down to 20 degrees. It would probably fracture, right? So I guess the only thing I can say is that we need to get away from zirconium-based cladding. We can use some other metals, but we need to get away from that zirconium water reaction that generates the hydrogen. Okay.
Do you anticipate that this event and the explosions that happen might spur the research?
Yeah, I certainly hope so. Yeah, I think that's. I hope in the U.S. I hope that's one of the lessons learned, that we need to spend some R&D money on getting away from the zirconium-based cladding materials. Yes.
So even though worldwide all the research in the last 60 years or so has gone into uranium-based reactors, there are potential alternatives. For instance, there was actually an operating thorium-based reactor at the Oak Ridge for quite a few years. And I wonder, every time something like this happens, it seems like there might be some possibility that people might rethink using uranium-based reactors, not only for this, but also because of terrorism-based concerns.
Yeah.
You're trained. Do you think there's any possibility this might spur other research?
Well, there's always, at a research level, there's always, certain a possibility to do non-uranium-based or thorium reactors. But is it going to happen? It's, just think of how hard it is to wean ourselves off of gasoline. How many years have we been talking about the hydrogen economy already? Is it going to happen? It's hard to. So that. When you think reactors, you think uranium, and that mindset is hard to change. We've invested already too much. So, DOE Department of Energy has looked at that. I mean, we would have to go through like a 100-year transition from uranium to a mixture of, uranium and thorium, or even plutonium-based reactors. But it would have to be phased in over, a 50 or 30 to 50 year. And is that going to happen with the Secretary of Energy changing every 4 to 8 years? I don't think so. Okay, so. Yes?
What's the way to decontaminate the area instead of just waiting for natural decay?
The natural decay can take.
I mean radiation.
Yeah, I mean strontium and cesium that are already been detected on the soil have half-life on the order of 30 years. And typically, to get down to 10%, it's an exponential decay, so it takes about 7 half-lives, so 200 years. before the radiation of the contaminated soil is low enough so that it's usable again. So you do need to do the cleanup. You have to take the topsoil off, and then so in some of the playgrounds, the kids really suffered the most because the kids in the school playgrounds that were in the contaminated area, they've now had to take off the topsoil, the 3 inches or so, and because the kids could not go out at all. Okay, they were confined indoors, so you can't go out to play. And that's already quite a job. I mean, even if you bulldoze and take off 3 inches off the top, where do you put that soil? That soil is contaminated. You cannot just pile it up in the corner of the playground and leave it there. You have to have a place to put that. And right now, I'm not sure that Japan is ready to, or has planned enough to put that soil somewhere else. Okay, so there's a lot of things that are going on. You know, everything is going on. So, yeah, it's you might not, like I said, you might not see it in the headlines. 60 days now, but you'll see it periodically for the next 10, 15 years. Yeah, I think. Okay. All right, thank you very much.